Hello and welcome, dear students. Today we will be discussing about one of the important topics of hydrology, which is having a very applicable aspects in day-to-day activity. Before having a detailed note of the topic, let us first have a fleeting look of the preamble of the concept. As we are very much aware that water is the fundamental component of the Earth's system and plays a crucial role in shaping landscape, sustaining ecosystems, and supporting a wide range of human activities such as agriculture, industry, and urban development. One of the central concerns of hydrology is understanding how rainfall is transformed into runoff. So this runoff rainfall process governs the movement of water from atmosphere to the land surface and eventually into the streams, rivers, and oceans. The transformation of rainfall into runoff is controlled by several interrelated physical factors. These include the relief and slope of the land, the nature and depth of the soils, vegetation cover, drainage density and pattern, and the characteristics of the underlying geological formation. Because these factors vary from one basin to another basin, each drainage basin responds differently to the rainfall. To study this time-dependent response in a clear and systematic manner, hydrologists rely on graphical tools. The most important which is the hydrograph. The hydrograph provides a visual representation of how river discharge changes with time following a rainfall event, making it easier to analyze basin response and compare different events. A hydrograph shows the variation of river discharge with time at a particular location after a storm. However, no two storms are exactly alike. Rainfall events differ in intensity, duration, and spatial distribution, which makes direct comparison between individual hydrographs difficult. To overcome this problem, hydrologists developed the concept of unit hydrograph, which provides a standardized way of representing basin response. The unit hydrograph relates runoff to a fixed unit depth effective rainfall taking place uniformly over the basin for a specific duration. The concept of unit hydrograph was basically introduced by L. K. Sherman in 1932 and has since become a cornerstone of hydrological analysis. Its popularity lies in its simplicity and practical usefulness. By expressing the direction of drainage basins as a single characteristic curve, the unit hydrograph allows hydrologists to estimate a runoff from other rainfall events of similar nature. So in this way, it provides a clear logical framework for linking rainfall input with stream flow response and forms an essential foundation for further hydrological studies. The second component is hydrograph and runoff. A hydrograph is a graphical representation that shows how the discharge of a stream varies with time at a particular location. It is one of the most important analytical tools in hydrology because it clearly illustrates the response of a drainage basin to rainfall or snowmelt events. In a standardized hydrograph, time is plotted along the horizontal axis, while discharge or flow rate is plotted along vertical axis. The overall shape of the hydrograph reflects the combined influence of rainfall characteristics and physical properties of the drainage basin. So far as a typical storm hydrograph, which can be divided into three main parts. That is the rising limb, which indicates the rapid increase in the river discharge following the onset of the rainfall. The slope of the rising limb, which indicates how quickly runoff from the basin reaches the stream channel, and basin with the steep slope. Impermeable rocks, thin soils, and sparse vegetation usually shows a steep rising limb because water flows quickly over the land surface with little delay. The peak discharge is uppermost point on the hydrograph and represents the maximum flow produced by the storm. This portion of hydrograph is of particular importance in flood studies because as it determines the severity and potential impact of flooding on surrounding areas. Engineers and planners pay close attention to peak discharge values when designing flood control structures and assessing flood risk. Next component is the recession limb, which is also known as the falling limb, which shows the gradual decrease in discharge after the rainfall has ended. This portion of the hydrograph reflects the slow release of water stored in the soil and groundwater systems. So the profile of the recession limb provides insights into the storage capacity of the basin and the role of subsurface processes in sustaining stream flow. Several runoff components make up the overall stream flow depicted on a hydrograph. The amount of rainfall that enters the stream channel directly over the land surface, particularly when the soil's infiltration capacity is surpassed, is known as surface runoff. Water that seeps into the soil, traverses laterally through the topsoil layers and finally enters the stream refers to as subsurface flow. Groundwater's contribution to river flow, known as base flow, is what keeps river flowing during dry spells with little or no rainfall. In unit hydrograph analysis, the focus is placed direct runoff, which consists of surface runoff and quick subsurface flow, but excludes base flow. A clear understanding of these runoff components is essential for correctly interpreting hydrograph and forms the basis of applying the unit hydrograph concept in flood estimation and watershed analysis. So far as the unit hydrograph is concerned, one of the most basic ideas in hydrology, a unit hydrograph, often called a unit hydrograph, is frequently used to analyze the relationship between rainfall and runoff in a drainage basin. The unit hydrograph is a very useful and potent analytical tool despite its conceptual simplicity. It is described as the direct runoff hydrograph created by 1 unit depth of effective rainfall, typically measured as 1 centimeter, that is eventually distributed throughout the whole catchment area and happens at a steady pace for a predetermined amount of time known as the unit duration or unit time. Effective rainfall as used in the hydrograph analysis is the percentage of total precipitation that directly contributes to surface runoff and then manifests as stream flow. The accompanying runoff hydrograph is expressed in terms of discharge, usually measured in cubic meters per second, and the unit quantity of effective rainfall is traditionally chosen as 1 centimeter, depending on the variables like the size of the drainage basin, the type of the form occurrence, and the availability of the rainfall and discharge data. The unit duration of rainfall can be chosen as 1 hour, 2 hours, 6 hours, 12 hours, or any other convenient time. So far as the essential conditions for the unit hydrograph formation is concerned, based on the definition of a unit hydrograph, 2 basic conditions must be satisfied for its valid derivation. Number A, uniform distribution of effective rainfall over the basin. The effective rainfall must be evenly distributed, especially across the entire drainage basin. This implies that if multiple rain gauges are installed within the basin to capture the rainfall variability, all gauges should record nearly identical rainfall amounts during the selected unit duration. Any significant variation in rainfall would result in an inaccurate representation of basin response. B is uniform rainfall intensity during the unit duration. The intensity effective rainfall must remain constant throughout the unit duration. For example, if the average rainfall over a basin is 12 centimeter, duration a 6-hour storm, a 6-hour unit hydrograph can be derived only if rainfall occurs at a steady rate of 2 centimeter per hour across the basin. If rainfall intensity fluctuates significantly with time, the resulting rainfall response cannot be represented accurately by a simple unit hydrograph. The next important aspect is assumptions of the unit hydrograph theory. The theory of the unit hydrograph is constructed on two major assumptions that simplify the complex rainfall processes. Number A is the principle of time invariance. This assumption states that the response of a drainage basin to a given pattern of effective rainfall remains unchanged within time. In other words, the shape and characteristics of the direct runoff hydrograph produced by a specific rainfall input are assumed to be the same regardless of when the storm occurs. Although basin conditions such as soil moisture, vegetation cover, and land use may vary seasonally, the unit hydrograph theory assumes these changes do not considerably affect the overall basin response. The next part is the principles of the linearity, that is the superposition and the proportionality. This assumption states that a basin's runoff response is closely correlated with the amount of effective rainfall. This implies that a rainfall event that produces twice the unit depth over the same duration will produce a runoff hydrograph with discharge values precisely twice those of the unit hydrograph if the discharge ordinates of a unit hydrograph for a given duration are known. Furthermore, if effective rainfall occurs in successive time intervals, the resulting direct runoff hydrograph can be obtained by superimposing individual unit hydrographs corresponding to each rainfall increment appropriately shifted in time. So far as the unit hydrograph of different durations is concerned, in practical hydrological studies, the duration of effective rainfall required for analysis often does not match the duration for which a unit hydrograph has been derived from an observed data. Since rainfall runoff records are usually limited, it is not always possible to develop a separate unit hydrograph for every desired rainfall duration. One common approach is based on the principles of the superposition. In this approach, a unit hydrograph of longer duration is obtained by adding together two or more unit hydrographs of shorter duration, each shifted to forward in time by length of the original unit duration. So the combined hydrograph represents the runoff response to continuous effective rainfall occurring over a longer period of time. This method is valid as long as the basin response remains linear and the effective of succession rainfall inputs can be added without interaction. Another widely used technique is the S-curve, or we can say that the S-hydrograph method. The S-curve is formed by summing a series of identical unit hydrographs of the same duration, placed consecutively at equal intervals of the time. The resulting curve represents the cumulative runoff response of the basin to continuous effective rainfall of unit intensity by taking the difference between 2 points of the S-curve separated by the desired rainfall duration and adjusting the scale appropriately so that a new unit hydrograph for that duration can be derived. Now, both these methods are firmly based on the assumptions of linearity and the time invariance of basin response. They are specifically useful in situations where rainfall and discharge data are limited. So, by enabling the transformation of a single unit hydrograph into hydrographs of different durations, these techniques greatly enhance the flexibility and practical applicability of the unit hydrograph concept in hydrological analysis. So far as the synthetic unit hydrograph is concerned, the development of a synthetic unit hydrograph is based on measurable physical characteristics of the drainage basin. These include parameters such as catchment area, length of the main stream basin, slope, drainage pattern, and overall basin shape. Empirical relationships are used to relate these basin characteristics to important features of the hydrograph, such as the time of the peak discharge and the general shape of the runoff curve. Using these relationships, the runoff response of a basin can be approximated even in the absence of the detailed rainfall and discharge records. Synthetic unit hydrographs are very essentially valuable for extending hydrological analysis to ungauged or poorly gauged basins. Although they do not achieve the same level of accuracy as unit hydrographs derived from the observed stream flow data, their simplicity, flexibility, and ease of application make them important and widely used tool in practical hydrological analysis under conditions of data limitation. Now coming to the derivation of unit hydrograph, which is very important in the concept of a unit hydrograph. A unit hydrograph is mostly accurately derived from an observed flood hydrograph produced by a storm that satisfies the basic requirements of relatively uniform rainfall distribution and reasonably constant rainfall intensity over the drainage basin. Such storms generally produce flood hydrographs with a single well-defined peak, making analysis and interpretation easier. Here I will just list some of the methodological steps which will be involved in the process of deriving a unit hydrograph. Number one is separation of base flow. The observed flood hydrograph consists of both base flow and direct runoff components. Base flow is first separated using suitable methods so that the ordinates of the direct runoff hydrograph can be obtained. Second part is the computation of direct runoff volume. The area beneath the direct runoff hydrograph is used to compute the total volume of direct runoff. Third is the derivation of the unit hydrograph ordinates. The discharge ordinates of the direct runoff hydrograph are divided by the depth of the runoff, which is obtained by dividing the runoff volume by area of the catchment. So the resulting discharge values plotted against the time represents the unit hydrograph for the selected duration. Smaller runoff depths can create considerable inaccuracies. Hence, the depth of direct runoff utilized in the derivation should ideally be equal to or larger than 10 mm for more reliable findings. So let us move to the applications of the unit hydrograph. The unit hydrograph is one of the most practical and widely applied tools in hydrology because it offers a clear and systematic way to relate rainfall over the drainage basin to resulting runoff at the basin outlet. By simplifying the complex rainfall runoff processes into a standardized response, the unit hydrograph helps hydrologists understand how a catchment behaves during and after storm events. This makes it especially valuable in both theoretical studies and real-world water resource planning. One of the main applications of the unit hydrograph is in the estimation of the flood hydrographs. When rainfall data for a storm are available, the unit hydrographs can be combined with this information to generate a complete runoff hydrograph. This allows engineers, planners to estimate how discharge varies with time, including the rising limb, peak discharge, and the recession limb of a flood. Such information is crucial for evaluating flood magnitude, timing, and duration, which are the key factors in flood risk assessment and mitigation planning. The unit hydrograph is also extensively used in flood forecasting and early warning systems. When short-term or real-time rainfall forecasts are available, the unit hydrographs enable hydrologists to predict the likely runoff response of a basin in advance. This predictive capability supports the issuing of timely flood warnings, helping authorities and communities prepare for extreme events. By improving anticipation and response, the use of unit hydrographs contributes significantly to reducing loss of life, damage to infrastructure, and disruption to economic activities. Another major application lies in design of hydraulic and water control structures such as dams, spillways, bridges, culverts, storms, drains, and flood protection works. Designing these structures requires a reliable estimates of design flood under extreme rainfall conditions. In many catchments where long records of stream flow data are not available, the unit hydrograph provides a simplified yet dependable basis for deriving design hydrographs. This makes it particularly useful in data scarce regions and developing areas. The unit hydrograph also plays a significant role in watershed management and planning. It helps us evaluate how changes in land use and surface conditions such as urbanization, deforestation, road construction, or the adoption of soil and water conservation measures affect runoff characteristics. By comparing hydrographs for different scenarios, planners can assess changes in peak discharge, runoff volumes, and response time, and can judge the effectiveness of management practices aimed at flood reduction and sustainable land use. In addition, the unit hydrograph supports water resource studies and environmental management by aiding in the assessment of the basin response under varying climatic and hydrological conditions. It provides a consistent framework for comparing different storms and catchments, thereby improving understanding of runoff behavior across regions. Overall, the unit hydrograph serves as a versatile and practical hydrological tool. Its wide range of applications from flood estimation and forecasting to structural design and watershed management makes it an essential concept in runoff analysis and water resource planning. By bridging the rainfall data and the stream flow response in a simple yet effective manner, the unit hydrograph continues to play a central role in applied hydrology. Let us discuss some of the limitations of the unit hydrograph. Although the unit hydrograph is widely used because of its simplicity and practical usefulness, it is important to recognize that it is based on several assumptions that may not always hold true in natural conditions. These limitations arise mainly from the complex and variable nature of rainfall runoff processes, which cannot always be fully represented by the simplified conceptual model. So as a result, the unit hydrograph must be applied with care and sound hydrological judgment. One of the major limitations of the unit hydrograph method is the assumption of the uniform rainfall distributions over the entire drainage basin. In reality, rainfall rarely occurs evenly across a catchment. Storms often show a strong spatial variations, with some parts of the basin receiving heavy rainfall while others receive very little or none. So this problem becomes more serious in large catchments or during convective storms when rainfall is unevenly distributed. The actual runoff response may differ significantly from that predicted using a unit hydrograph developed under assumptions of uniform set of rainfall, which leading to inaccuracies in peak discharge and timings. Another important limitation is associated with the assumption of linearity between the rainfall excess and runoff. The unit hydrograph theory presumes that runoff is directly proportional to effective rainfall and that hydrographs can be scaled up or down accordingly. While this assumption is reasonably valid for small to moderate rainfall events, it often fails during intense or long duration storms under extreme conditions. Infiltration capacity may be exceeded, surface storage may become saturated, and flow paths may change. These factors introduce non-linear behavior, meaning that the Bayesian response cannot be accurately represented by simply multiplying a unit hydrograph. Human activities such as urbanization, deforestation, construction of reservoirs, and channel modifications can significantly alter runoff characteristics. When such changes occur, a unit hydrograph derived from historical data may no longer represent the present day behavior of the basin. A single unit hydrograph may not adequately capture the diverse runoff responses occurring in different sub-areas of the basin. So in these situations, more detailed method of distributing hydrological models may be required. So these limitations underline the importance of using the unit hydrograph with care and caution. While it remains a valuable and widely accepted tool in hydrology, especially for preliminary analysis and data scarce regions, its results should always be interpreted in light of the assumptions involved. Understanding where and why the unit hydrograph may fail helps us ensure more reliable flood estimation designs and watershed management decisions. So this was all about today's module. Hope you have got through well. Thank you very much.